Hi, good afternoon. This is our last lecture. We still have the publication, how to publish your data, but I might also upload another lecture, maybe from a colleague. Uh, Now we have data analysis and interpretation that will help you towards finalizing your analysis. Again, I'd like to reiterate that for those who are not able to collect data, what I would expect from you for the presentation is to present the background, a justification, any gap in the literature. So what is your what's your rationale for the study? How did you do the study? How did you build at least the study? What kind of concept you measure? And then challenges and lessons learned after you submitted to IRB and got IRB, because I believe that few of you were not able to get to the data collection phase. But if you have collected data, no matter how big your data or how small is the data, I would expect you, if you have some data, to do analysis, and we were going to discuss all the steps in the analysis and interpretation. You have seen before the slide, we can actually divide our statistical analysis into two main components: a descriptive univariate component and an analytical component, which is a bivariate and multivariable analysis. So in the descriptive component, we're looking at characteristic of participant and the characteristic or the distribution of the main variable of my study, the dependent or the outcome, and the exposure. And the analytical and bivariate, we start looking at association, two variable at a time, that we call bivariate, or we take the outcome and we associate it with more than one simultaneously, and we call it multivariable statistical analysis. So if we're talking about the univariate analysis, so it means that we are dealing with one variable at a time, and the analysis of one variable at a time allows us to describe who's in the sample and to make inference about a larger population. We can represent the result by proportion or mean, depending on the nature of the variable. But it allows us also to look at every variable, whether we have enough observation, enough data in different categories. So do we have variability? Do we have a dispersion? Are everybody alike in terms of a certain variable? Are all female? Are all educated? Are all married? Do I have enough people married and not married? Because this would help, allows me also, if I have several response category, maybe to group category into each other. At the same time, looking at one variable at a time, especially the continuous variable, would allow me also to identify unusual data. What I mean by unusual data is outliers, which are data that could be wrong data, but it could be as well exceptionally high or exceptionally low data, and think about what to do with them so they won't affect my result. Looking at one variable also at a time helps me decide if I want to exclude any variable, if I have those knowledge questions where I don't know what to do with it, and think about how to handle missing data in case some of my data don't have any information. So people miss to fill it, or they just skip the question. So it's basically, you have two output from the univariate analysis. The first one is the profile of the sample, or you can call it characteristic of the sample or distribution of the sample based on basic sociodemographic variable. But another main outcome is you get the estimate of a prevalence or the mean of your main variable of interest. So if I'm interested in rheumatic arthritis and looking at factor associated with rheumatic arthritis, before looking into association, I would like to calculate how many or what is the prevalence of rheumatoid arthritis among my sample. And then I would like to also look at what is the distribution of the factors of these of arthritis. If I'm looking at, let's say, obesity in terms of body mass index, in terms of kilogram into meter square, I would like also to look at the distribution of obesity among a certain population with its 95% confidence interval that I'll talk in a minute. So therefore, for univariate analysis, it's good to distinguish between the categorical data, where a summary measure or the analysis would be simply frequency distribution, and the computer SPSS will give you an output where you have the frequency, which is the absolute value, and the percent or the valid percent, which are the proportion of every person of these in the total sample or in the sample without the missing. So here we have 2 missing, it means 2 without any value on a nationality. So therefore, the computer will generate, SPSS will generate percentages with the missing and without the missing. And this is the valid percent. And how we interpret this? We interpret that most of the respondents were Lebanese, for example, if we're looking at this type of variable. And if my variable, my univariate, again, we are under univariate analysis, so the variable is continuous. So the way we describe that variable is to look at the measure of central tendency, which means which means I need to look at the average or mean, median, and mode. Again, I have provided the command that you use in SPSS again, so you don't have to go back to my to the handout that I gave you on SPSS. So you analyze descriptive statistics frequency, or you can analyze descriptive statistics descriptive. That will give you mean, median, and mode. And the first one can give you the mean, standard deviation, minimum, and maximum, which are what? Which are statistics or quantity, statistical quantity to measure variation. So therefore, in addition to measures of central tendency for a continuous variable, you need to present as well measures of dispersion. So when you present, for example, mean age, you don't only present the mean age, but you present as well its standard deviation. So you would say the mean age is, for example, here 19.8 plus or minus 1.67. You can also represent it by variance, interquartile range, or a minimum and a maximum. This is also the minimum and the maximum also provides you with a measure of variation. So what else in terms of, we said that univariate also can provide us with information on outliers. So if I have a measure that's extremely high or extremely low, the way I can check it is by doing a box plot. So graphs, legacy dialogues, box plot, or I can do analyze, explore. This is something I did not put on the slide, but you can do as analyze, explore, and the explore command gives you the box plot. You can do a box plot for all the data, or a box plot like here, according to the main variable, that's age, but you can look at the age according to gender. And then you see here that among the male, you have one extreme value. So most of your data are between, let's say, 18 to 22, but you have one guy who's around 45. So this might be an error in your data, or this might be really somebody who's undergrad, but for example, but who came back to university and he's a 45. So what do you want to do with this 45? Because it will push your mean towards a high value. So that's why it's good to look at outliers. So this is, so in the, as we said, in the univariate, so you describe, you present proportion, means, median, etc. But at the same time, when you think about your outcome or your exposure, you're giving an estimate. So you'd like to estimate the proportion of students who are smokers. You want to estimate the proportion of body, not the proportion, the mean body mass index among students in medical school. So with these point estimates, we call them point estimate, it's good also to provide an interval estimate. So therefore, with every estimate which is not the true value, but based on a sample, it is good to quantify it, not to quantify it, to add to it an interval estimate, which is a 95% confidence interval. For example, the mean here is, the mean was 19.98 with a standard deviation of 0.65. So, and the confidence interval are between 18 and 21. So we can say that we are 95% sure that the real population mean, which is the real mean age of the population, lies between 18.66 and 21.29. Just to note that when you say to people, for example, the prevalence of smoking is between 12% at AUB and 50%, this is really very wide confidence interval. This means that you are not very confident what exactly is your the true prevalence. So this means that the wider the CI, the less precise. So again, when you present your sample, when you present prevalence of certain diseases, when you present mean score on for example, on a certain test, on HbA1c or whatever, among your sample, it's good always to put a 95% confidence interval to that particular estimate, be it a continuous, a mean, or a proportion. This is the way usually we present the univariate. So variable, frequency, percentages. This is a general table presenting sociodemographic information like gender, age, and education. You can add medical information. Again, this is N and percent, and here is a mean and standard deviation for the age. Of course, you can as well present your age as a categorical variable. So this is another one, another table that presents description of the study sample. Again, the way it's presented as this is a study on looking at autism and presenting basic information about the child and the mother. So you note here we have characteristic of the child, basic characteristic, and this is a pure descriptive table. So we have 537, so we have 998, and we have 53% who are males. We have a mean age of 27.6. We have 27.6 months, excuse me, because these are children. Their distribution with respect to whether they're coming from Beirut and Mount Lebanon. You have another part of the table which is parent sociodemographic information, education level of mother, of father, professional status of mother and father. And a note here that the number do not always add up to the 998 because in some variable we have some missing data, so we note that they don't always add to 100%. So this is what it is. So univariate is to describe your data, trying to maybe manipulate some of the variable based on the univariate distribution, but as well presenting your sample and give an estimate of your main variable of interest. So if your variable of interest, what is there stigma for mental health among the Lebanese population? So you want to present the attitude of mainly the attitude in terms of description. How many have positive, how many have negative attitude. You would like to present how many have knowledge about mental health, the level of knowledge, high, low, etc. So this is univariate. But when it comes to bivariate, this means that you want to start looking at association between variable. So is depression associated with age? For example, burnout associated with being a medical student versus non-medical student have less burnout. So you'd like to look at independent, if you have several exposure, are they related to each other? You can also do bivariate to compare two groups, just compare. So take cases of lung cancer and compare their smoking with compared to smoking in lung cancer, in non-lung cancer patients with our controls. You can compare treatment, no treatment, exposed, non-exposed, look at correlation. So the type of bivariate analysis, which means analyzing two variables together, depends on the nature of the variable. When we talk about the nature, it means is it categorical or continuous? Is it qualitative or quantitative? So if we're looking at two categorical variables, we use cross tabulation. It's like depression, yes, no, with male, female. One continuous variable and one categorical would be comparing mean. For example, if I have a score on depression with gender, so it will be mean score on depression between male and female. The other one was depressed, yes, no, male, female. The second one would be score on depression and male, female, which is the categorical. Or you can have an association between two continuous variables, weight and height, score on depression versus IQ score, score on depression versus your average, your school average, your GPA, for example. So this is a kind of continuous variable, so bivariate. So let's take this example of two categorical variables. So we wish to check if people who exercise are less prone to be admitted to the hospital due to cardiovascular problems. So therefore, the independent or the exposure variable exercising, yes or no. And the dependent variable is admission to the hospital, so or hospital admission due to cardiovascular problem. So I gave you the SPSS command, which is analyze descriptive crosstab, and the statistics that you want to do is a chi-square test here, and the cells you choose the percentage that's needed, row, column, or both. Most importantly here, I did not provide you with the percent, but what you want to compare are those who exercise, so sportive, versus the non-sportive, so those who are athlete, non-athlete, and how many of them are admitted. So 5 out of 19 and 8 out of 11. So if I am to ask the SPSS to provide me with the percentage, I always ask the percentage in the direction of my independent variable or my exposure variable. So this being said, what I want to look at is to test whether this association is significant at the bivariate level. So the computer would ask for a chi-square test. So this chi-square is, you look at the Pearson chi-square, 6.111, and this is 0.013. And this means that the association between the two is statistically significant. It means hospital admission is associated or affected by exercising status, and with a p-value of less than 0.05, which is 0.13. But please note that here underneath the table, it says one cell have expected count less than 5. So in a chi-square test, so to use the Pearson chi-square, your expected value should all be more than 5 and more. So since this one is 4.77, and I have only a 2 by 2 table, and there is no room to collapse further my category, so therefore I look at the Fisher exact test. So this corrects for small sample size. So the Fisher exact test is telling me that the association is statistically significant with p 0.23, and therefore there is a statistically significant association between exercising status, so doing sport, and hospital admission. If one of my variable is categorical and the other one is a continuous, so I'm comparing means. So example, if I want to check if the mean age is the same for adult living in Beirut and Mount Lebanon, so the SPSS command is analyze, compare means, independent sample, because these are two different samples in Beirut and Mount Lebanon. So the test is age, the variable, the testing is age, which is like the dependent age. It depends on being in Beirut or Mount Lebanon, which is Muhafaza, and OHA stands for Muhafaza or Governorate. So again, that comparing means gives me first a descriptive table, which tells me that the mean age in the first muhafaza is 40 with this 4.2 standard deviation, and the mean age for the second muhafaza is 29.67 with a mean of 4.27. It looks like in muhafaza 1, the mean age is people are older. Let's see, is it statistically significant? So this is the independent sample test. And the equal variance, so we have two tests actually here. We have the Levine test for equality of variance and the t-test. So the Levine test is a condition to check whether the standard deviation or the variance between 1 and 2 are equal. So if they are equal, we use the first line, and if they are not equal, we use the second line. So this Levine test, it tests whether the variances are equal. So if the test is not significant, it means the variances are equal. So therefore, I take that test and I check its significance. If the equal variances, if this is significant, this means that I take the second line and make my conclusion. And therefore, here the Levine is 1.5, the P is 0.227. This means that the variances are assumed are equal. So so is there a significant difference now between mean age among the two muhafazat? Yes, because here the t-test is 6.6, the significance is 0.000. So this mean difference of 10.33 is statistically significantly different. And we see the confidence interval of the difference does not include 0, because if there is no significant difference, it means you expect that the population difference would be 0. So here you don't have an overlap with 0, and therefore the two governorate are statistically significantly different in terms of age. Okay, so now in case of we have one continuous variable, but the categorical is more than one category. Okay, so the example is if we want to compare the mean age of the nurses in multiple hospital. In the previous slide, we had the age in 2 muhafazat, in 2 governorate. Here we have multiple hospital, UBMC, Hotel Dieu, Saint George, and Sacré-Cœur. So therefore, we are comparing 4 means. So the hypotheses are the means equal, mean age in the population, or at least 2 of the means are different. So because we are looking at not 2 sample, we are looking at 4 means, sorry, not 2 means, but 4 means. So the proper SPSS command is analyze, compare means, and one-way ANOVA. And then if we want to look at which of the 2 means are different, is it Saint George versus Sacré-Cœur, Hotel Dieu versus Saint George, you do something called post hoc analysis, which is Bonferroni and Sheffy. So therefore, my dependent list, again, age, dependent because I'm testing for age, and my factor is hospital. So it gives me the ANOVA table. The ANOVA table gives me an F-test, which is statistically significant. So I look at significant means this is the p-value. So the test is statistically significant, and therefore I reject H0, which means that at least 2 of the mean age are different. And to check, as I said, which means are different, you can do Bonferroni or Sheffy test. So you can do something called post hoc analysis to know which of the 2 means are statistically significant. And we said bivariate are categorical, continuous. And if you want, you can look at, instead of simple association, you can look at correlation. And correlation means when you have 2 variables that both are continuous. So we want to study the correlation between age of medical doctors at the hospital and their monthly salary. So we analyze, correlate, bivariate because the correlation is between 2 variables. And it gives me a matrix. So this is age versus age, of course, is 1. Age versus salary, this is 0.366, and therefore the correlation is 0.366. Correlation, or R, or correlation coefficient, in the population we call it rho, but in the sample we call it R. It goes from -1 to +1. -1 is a very strongly perfect correlation, negative correlation. 0 is no correlation, and 1 is a perfect positive correlation. 0.3 is a moderate, weak to moderate correlation. But at least this weak or moderate correlation is significant. We look at the p-value, and it says that the p-value is 0.047, and therefore it is statistically significant. So this is another way of looking at association between 2 variables by doing correlation if the 2 variables are continuous. Okay, and now we do we did the univariate, the bivariate, and now we want to look at multivariable analysis, which using regression. So multivariable analysis meaning that we have one main outcome variable or dependent variable, and this is regressed on one or more independent variables. So it is used therefore to estimate and quantify the relation of a dependent variable or an outcome and one or more independent variable. We're going to call the independent x1, x2, x3, etc. And the dependent variable is y. So why do we use regression? So regression, one is that it is used to predict the dependent. But most importantly, and this is not in here, so when you put all these variables together, you produce adjusted measures of association. So when you look at, let's say, depression and gender, and you do your chi-square, and you get an odds ratio. This odds ratio is usually called an unadjusted odds ratio. But if you want to account for other variables other than gender, and you do a regression where your outcome is depression, age, gender, socioeconomic status, so on and so forth. So the association now between depression and gender is controlled for other variable in the regression. So therefore, we call the OR or whatever measure of association that are that are generated from a regression, we call them adjusted measures of association. Okay, when we have a regression and we put only one independent variable, we call it a simple regression. And when we put multiple independent variable, we call it multiple regression, corresponding to multivariable analysis. So the regression, it depends only and only on the type of response. So the response, it means the y variable. So if y is continuous, we use linear regression. And of course, there are assumptions for using linear regression, normality, homeostasticity, that you have to really reflect on with your mentor or with the biostatistician. But usually, if you have a nicely shaped, normal distributed outcome with some independent variable, you use the linear regression. If your y is binary, like disease, non-disease, depressed, non-depressed, cancer, no cancer, you use binary logistic regression. So it's another regression that model the probability or the odds, the p over 1 minus p. And if your outcome is a count, you use Poisson regression, which is like number of patients in a hospital. I'm going to address two types of variable, but let's look at this one. So we look at the independent, so multiple regression. So how we these are still general issues about regression. So if we have when we look at the independent variable that were significant at the bivariate level, so how do you usually do the analysis? As we said, we start with the univariate, we shape, we manage my data, and then I start looking at the bivariate association. So those associations that are bivariate, that are significant at the bivariate level, or the independent variable that shows statistically significant association with outcome at the bivariate level, I move it to the regression, or I move it to a step which is the multiple regression. Which one I choose, usually which one are statistically significant and need to be taken. We are, biostatisticians are conservative, and we don't take only p's that are less than 0.05, but we take any independent variable who's associated with a dependent with a p-value of less than 0.2 to be more inclusive and more conservative. And then we regress all the x's, so all the independent that have a p-value of less than 0.2, again at the bivariate level on y. So we regress x on y. So we have several independent, one dependent variable, and then we look at the significance of those variables at the bivariate and the model. So we compare the unadjusted, which are the crude based on the bivariate, to the adjusted that are in the model. And we can then build a very simple model, we call it parsimonious model, where we can only keep those that were significant and remain significant in the multivariate analysis. Okay, and we can add one variable at a time, and then taking one of them at a time to check whether the significance is changing, yes or no. So, and then which variable to keep. Sometimes even if the variable are not very much statistically significant, but you'd like to keep it because it's clinically significant, and you might want to keep it in the model. And sometimes it's always recommended to keep age and gender, which are universal confounder or universal control variable, to keep them in multiple regression, even if they are not significant at the bivariate level, because there's always have some residual confounding due to age, or some partial confounding due to age and gender that we'd like to keep. So we said I'm going to address two types of regression. The linear regression, where your y is continuous. So we regress all these x1, x2 on y. So the example is Jensen and Keller used age and education level to predict the capacity to direct attention and capacity to direct CDA in elderly. So this CDA is measured in terms of scoring. So higher score of CDA show better attentional functioning. And we want to look at age and educational level and their association with CDA. So X1 is age, X2 is educational level, age and educational level, and Y is CDA, which is a score on capacity to direct attention. So the example here, data are collected on 71 community dwelling, older adult with normal mental status, and we want to test if the model is significant. This means that if I enter B1 and B2, if I enter X1 and X2, do X1 and X2 significantly predict Y? So does X1 and X2 significantly predict Y? And we look at the test statistics, which is overall F-test. And we can actually not only do the overall, whether the overall regression or model is significant. So again, if I go back, so we have an overall test to say that the model is significant or not. So at least one of the betas or one of the regression coefficient is significant from 0, or we can test for every single beta, whether every single beta are significant. So we test each variable in the model. So, and the model gives me a statistical association for each one, okay? We in the multiple linear regression, we look at something called adjusted R squared instead of R squared, which means that this is the proportion of the Y that is explained by the variable that I have put. So I have an R square, which is the simple model, and the adjusted model is when you add independent variables. So how much of the X1 and X2 explain the variation and the dependent variable. So let's take this example. So again, the SPSS command is analyze, regression, linear. You have to specify what's your dependent, which is your test variable, which is CDA, and what are your independent, which are age and education. So testing the model. So we said testing the model and testing every single variable. So testing overall, is the model statistically significant? So is the model statistically significant is based on F-test. So the F-test is 20 and the P is 0.00. So this means that overall the model is significant. So adding those two variables together are explaining why. Okay. Now let's see each variable. So what multiple linear regression provide me is it provides me with a coefficient for every variable. So this is a unstandardized. I can use actually both, minus 0.18 and 0.611. And so age is a continuous variable. So this means that for every increase in 1 year of age, I have a decrease in the capacity, whatever, the CDA, a decrease of minus 1.84. Is it significant? Yes. Here is the statistical significance, excuse me. So it is significant. Okay, this is the T, which is beta over standard error of beta. The T is minus 0.37, like any T statistics, and it is significant. This means that age controlling for education explains or predicts significantly the CDA scores. If we look at education, 0.611, this regression is for every, as we increase age, as we go from one category of education to another, there is an increase in the CDA score, and this increase is statistically significant again. And this we say education controlling for age. So we can read it differently also for beta 1, which is for the coefficient regression, which is the amount of association between X and Y. So for two people with the same educational level, for each year increase in age, CDA decreases on average by 0.184. B2 is for two people of the same age now. It means controlling for age, for every year increase in educational level, education was here in educational level, CDA years in schooling, CDA decreases on average, it should be CDA increases on average by 0.611. Okay, so adjusted R square. So this is the R square, adjusted R square. So the adjusted R square is 0.352, which is not very low, which is acceptable. So these two variables explain 35.2% of the total variability in CDA. It means that we need to enter more exposure variable to understand CDA. Again, as I said, maybe because we forgot to account for other variables that might affect CDA. So the multiple logistic regression now. So now we are looking at a variable as a dependent variable that's binary. So the y is binary. It means we compute it with a probability. So either you have the disease or you don't have the disease, you have the attribute or you don't have the attribute. And the explanatory variable, the axis could be continuous or categorical. It doesn't matter. What matters is that when you use the logistic regression, it means your response is binary. Okay, knowledgeable, not knowledgeable, a positive, negative attitude, depressed, non-depressed, cancer, non-cancer. So the model is, so we model the log of the probability over 1 minus the p of the probability. So 1 minus, so it is the loss. The log of odds is a linear combination of alpha, the constant, plus b1 x1, b2 x2, pk xk. So first we need to test for them, again, the model significance, similar to the multiple linear regression. We measure whether the overall, all the axis or all the model is statistically significant by looking at the likelihood ratio, which is equivalent to a chi-square test, and we look at its p-value. So it's just saying that either all the betas, so all the coefficients are of the independent are zero, or at least one of them is different from zero. It means none of the covariate is associated with y, or at least one of them is associated with y. Then we can check, or each variable, so each beta, if it is significant, equal to zero or not equal to zero, and we do a test of significance for each one of them. And last, we need to check if the model fits the data. In the multiple linear, we look at the R-square, adjusted R-square. Here we look at the goodness of fit of the test, which we call Hosmer and Lemeshow, which tells me whether the model as H0, it fits the data or does not fit the data. So if the p-value is not significant, it means it fits the data. If the p-value is significant, it means it does not fit the data. So this is an example looking at the relationship between GI and eating cake, vanilla ice cream, chocolate ice cream, and age and gender. So the GI, having GI problem is the binary variable. So this is the first one, testing the model significance. So this is the chi-square test. And the chi-square test for the model is statistically significant. It means overall, those independent variable explain statistically the model. And then we look at the multiple logistic regression provides me with a table where I have the beta, but importantly in the multiple logistic regression, it gives me, if I take the e to the beta, the e exponential of beta, this is the odds ratio. So these are the odds ratio. So this means that for somebody who has eaten ice cream, they have 29 higher odds compared to those who did not eat ice cream to have a GI controlling for other variable in the model, and this is statistically significant. Other variable are not statistically significant. The other variable is gender. So I think maybe male or female, I'm not sure, but as we're talking, so could be male or have 4 times higher odds of GI than female, controlling for other variable in the model. Is this particular beta significance? Yes, it is significant. So these are called adjusted ORs. Why adjusted? So variable, so if you have a 2x2 table, what you can generate are odds ratio. If you're doing bivariate, you get an unadjusted odds ratio. And if you even do simple logistic regression, entering one variable at a time, you get the exponential of beta, which are unadjusted. When you put all the variable together, you get adjusted odds ratio, and these are statistically, so the two statistically significant. So at the end, if I want to make a statement, I would say that only 2 variables are statistically significant, and they are associated with GI, which are taking vanilla ice cream and gender. So these are associated. So this is the interpretation, and you look at the confidence interval, it does not include one, and this means they are statistically significant. So now I will move to another link to talk about reporting of results.